In our last video, we covered the Euler-Lagrange equations, which give us the conditions that are necessary to minimize a path integral on a certain interval. So in the case of what I have underlined in blue right here, we're going to be minimizing the path integral of f with respect to an independent variable x over some interval of x1 to x2 or something like that. And so it turns out that one of the key fundamental laws to nature is that this integral, called the action integral right here, is going to be stationary as well. And the action integral, the action is defined as the integral over 2 points in time, so time is our independent variable, of something called Lagrangian. And the Lagrangian is a function of a few coordinates. I can't spell. Lagrangian. And Lagrangian is the function of some coordinates and their time derivatives. So these are generalized coordinates. Now, generalized coordinates, what they do is they define the configuration of a system. So for example, if I had a particle that was moving in 3 dimensions, our generalized coordinates could be maybe something like x, y, and z, or maybe something like, I don't know, in spherical or cylindrical coordinates. Basically, you would have 3 generalized coordinates to describe the configuration of this system. Similarly, if we had a pendulum of this length, then the generalized coordinates that we would have if this pendulum lies in a plane would be maybe some angle of the pendulum and then also the radius of the pendulum. We'll go back to the pendulum later. It's an interesting example. But what the Lagrangian right here is defined as is the difference between the kinetic energy and the potential energy of a system. So the fact that this right here is stationary, that's Hamilton's principle, or Hamilton's principle of least action, or maybe principle of stationary action, whatever you want to call it. The path integral of this quantity right here, the difference between kinetic energy and potential energy, over some interval in time, is going to be minimized. And that's just a fundamental law of nature. This can be used to construct mechanics in the same way that Newton did. For now, let's consider what the Euler-Lagrange equations would look like for action. Well, we would have dl over d qk minus d over dt, because times are independent variable, of dl over d q prime k equals 0 for k equals 1, etc., all the way until n. So for a system of n generalized coordinates, you're going to have the same number of Euler-Lagrange equations to deal with. And that's why it's generally best practice to try to get the least number of generalized coordinates as possible. So let's consider a particle that moves unconstrained in 3 dimensions, subject to a net force. And that net force is going to change over position. So let's say maybe we have this particle right here, and its position, we'll define it as x. And then we have a force that is a function of x, so it changes. It can change as x changes. So the particle's kinetic energy is, of course, going to be T equals 1/2 mv squared equals 1/2 mx dot squared. And the potential energy is going to be a function of x as well. So if we consider these little partial derivatives right here, first we're going to take the partial derivative of the Lagrangian with respect to x, and that's just going to be equal to minus the partial derivative of potential energy with respect to x, because when we take the partial derivative of the Lagrangian right here, the t is going to vanish because it's not a function of x explicitly, and we're just going to be left with this right here. And what you may recall is that force is defined as minus the gradient of u. So this is pretty much just saying, oh, this is equal to the force. And so for our other partial derivative, we have dl over dx prime, and that's just going to be equal to the derivative with respect to x prime of t, because u is going to vanish when we take the derivative of the Lagrangian with respect to x prime, because it does not mention x prime explicitly. And when we do that, we're just going to get that it's m times the velocity, which is just the momentum. And from that, we get that force equals the derivative with respect to time of momentum. If we plug these partials right here into our Euler-Lagrange equation, which these are called Lagrange's equations, by the way. So basically what we've seen here is that the Lagrangian formulation of mechanics is equivalent to Newton's formulation of mechanics, because you'll notice right here, this is just another way to say Newton's law, because we're just saying d over dt momentum. Well, if mass is constant, that just d over dt mass times velocity, which is just mass times acceleration. And we can do this, and we can do all of this in different dimensions as well. But what I'm trying to get at here is that Lagrangian formulation mechanics has no fundamental difference to Newtonian mechanics. They're both equally valid models of the same phenomena. Isaac Newton saw the universe in terms of forces, and Lagrange saw the universe in terms of fields, like potential fields that we move through. This right here, this partial derivative, is defined as the generalized force, and this right here is the generalized momentum. If we work in polar coordinates, then, like, for example, r phi, then the component of generalized force in the phi direction right here is going to be equal to the torque. And then if we have the the partial with respect to phi prime, that's going to equal, oh, I'm reusing L, but let's just say angular momentum. So what I'm trying to get at here is that generalized forces and momenta need not necessarily have the dimensions of force and momentum. So when the Lagrangian is independent of a certain coordinate, then that coordinate is sometimes said to be ignorable or cyclic. What we mean by this is that the Lagrangian is unchanged or invariant when the this ignorable coordinate varies when you have all the other generalized coordinates held fixed. Thus, we can say that if the Lagrangian is invariant under variations of the coordinate, then the corresponding generalized momentum is conserved. And if momentum is conserved, then that means there's no external forces, of course. And it's generally a good idea to choose coordinates so that as many as possible are ignorable and that their corresponding momenta are constant. This is literally equivalent to saying, oh, we want to deal with the least amount of forces, right? So now we're going to move into constrained systems. We can define degrees of freedom as basically the number of coordinates that can be independently varied. So it's the number of directions in which the system can move from any given configuration. If we have 3 points right here, this point can move in x, y, and z. This point can move in x, y, and z. And this point can move in x, y, and z. Then we say that there are 9 degrees of freedom, because this particle can move independently in this direction, or this particle right here can move independently in this direction. So a particle that is free to move anywhere in 3 dimensions has 3 degrees of freedom, and a system of n particles has 3 times that degrees of freedom. When the number of degrees of freedom of a particle, an n particle system in 3 dimensions is less than 3n, we say that it is constrained. For example, if we were to consider, it's just an example of a constrained system. If we were to consider a pendulum in a plane, just to resolve this, let's consider a pendulum in a plane. So we have our pendulum, our top right here, and then we have our little ball. So this only has 1 degree of freedom, because if we consider polar coordinates, we can maybe say that what can be varied right here is phi, but then this r right here, this radius, this distance from this point to from the point of the pivot point to the ball, Well, that's always going to be constant. So that's what's constraining the length. It's constrained by the length of the string. And a system is holonomic if it has a number of degrees of freedom equal to the number of generalized coordinates needed to describe the system's configuration. So for example, we would say that this right here is a holonomic system because we don't really care much about this radius. This is more what matters because that's what's needed to describe the system's configuration. Holonomic systems are easier to treat than non-holonomic ones in general, so when I come out with the examples, we'll only be treating holonomic systems, although there are problems with non-holonomic systems. Next video, we will cover Noether's theorem, so we'll see you then.